Okay. So, hello all. Yes, that's week two. We'll wait for 2 more minutes and then we'll start this week's session. I'll just complete my introduction till then. So, I'm Jagriti. I'm a PhD scholar at IIT Gandhinagar. I have officially entered my fourth year as of yesterday. So, I'm a PhD student in Biological Sciences and Engineering Department, and I work with Professor Carla Mercado Shekhar in the Muse Lab, Medical Ultrasound Engineering Lab. So I'll just wait for 2 more minutes and then we'll share. So this is like our second week for the course NPTEL course on techniques on material characterization by Professor Shibayan Roy from IIT Kharagpur. So the last week we saw basics, optical microscope, differences, and then solved assignment questions related to numerical aperture, convergence angle, something related to aberration. This week also will go in a similar way. First 2 weeks are like for the TAs to see that, okay, about the audience, and then they'll cure the content accordingly. And then if they feel that, okay, they need more depth into the material, accordingly add, accordingly reduce the material. Since we have two TAs and that to be two recurring sessions, like 3 to 5, 5 to 7, you all likely you said in last weeks, I don't know, I haven't yet received anything from NPTEL yet. So it's fine. And even if you're not able to attend the session online, you can always go to the YouTube link and then attend it from there or see the recordings from there. Only thing that you miss out on is the live discussion. Well, you can always join in whenever you want to. So I will like we don't have any restrictions as on when to join and when not to. Okay, so I guess with that, likely I'm audible to everyone. If not, let me know if you think I'm just lip sync. And then now I'm about to share my screen over here. There are my slides. I hope those are visible to everyone there. Okay. So just present. Okay. So towards this microscope that we saw. Now what was this? Okay, let's just take a pen. So as in last week, we just saw a simple schematic of a modern microscope. So it's for an optical microscope and how it works. But this week, we are going to see everything into detail, different modes of it, how it's like different kinds of microscopy also, and it's like how and when it would be useful, which kind of specimen you would find it useful to image it and all. So everything also, sometimes it depends on the specimen, sometimes it depends on the type of imaging that you want to do. Sometimes it depends on the type of structure or features that you want to find in that particular specimen. So there are different kinds of microscopy for the same. So if you see here, like you would find some things which are like very known to you, something that is nothing but from where your light source is being generated. So it can be a lamp. Now that lamp can be any given lamp. Let's assume that it's like there are again different types of lamps here. So let's just assume a generalized one. Then you have different filters for light. Now in this case, the filters can be just none or one specific filter. The filter can change if you need some fluorescence imaging into it. Then you have this different focusing knobs. Now, why are these focusing knobs? To adjust in between the planes of imaging where you want to image. Then you have the condenser lens here. So starting first, you always have the first one. What you have is nothing but called as the condenser lens, right? After the light source. So this is nothing but this kind of lens will illuminate your object or your specimen. The second one you have is your objective lens. Now, what is this objective lens? This is the one that will eventually go towards the final end, will take up light from the object that is being reflected and all. And the third one is your projector lens, one which is responsible for image formation, right? So these are like the three type of lens you have, and based on three different lens where it's placed, how its position is with respect to the specimen, you also have different kinds of imaging over there. Okay, then you have this stage is here. Now, why is the stage provided to you? Now, this stage is nothing but so that you move your sample from up to down. Sometimes what happens is you just take your sample in a cover slip, oh sorry, in a glass slide, and then you have it in the center of something. Then you have a cover slip on top of it. Now, you just want to image this specific area, but your stage involves this big area. So now you want to move your specimen, take your readings in between different samples or different planes. So then you move it along, right? Then you have this objective lens. Now this objective lens are nothing but, now sometimes what happens is you cannot so this distance is where it's fixed. So this distance from the field, this distance from the stage, and this distance from the lens, it's always fixed. With respect to different objective lens is fixed, but we cannot always change it. So how do you change it? One, you can change nothing but the magnification of these objective lens. So you can have these in different ranges, can be 20x, 40x, 60x, 100x at max till optical microscopes. Okay, and then what you can change, the other thing is also the position of this particular motion. This motion, how you or where you want to go around. The other thing you can change is nothing but the focal length. Now this focal length and magnification will be the ones which can be changed. Okay, these two can be changed if you want to focus or if you want to change your field of view where you are trying to look at. Okay, there's one more thing that you can change is through this part. What is that part? Is the aperture. The amount of light that is passing through your aperture and how it's focusing on your sample. So that aperture, the size of the aperture also you can change. Based on the aperture, what will happen is like you all can unmute yourself and say whenever you want to. But based on the aperture, something changes. Your numerical value, this particular value, it also change. Now, based on this, it affects your resolution. So this is how everything depends on one and the other thing, right? Now, this is the final thing where you just see where your sample is about. These are the projector lens, which will nothing but eventually make up an image. And so nowadays, in all of the modern microscopes, they have their own digital cameras. So through the help of this digital cam, you also have a software connected next to the digital cam. Now through that particular software, you can adjust the threshold, the light, you can adjust the exposure settings, you can set a scale bar, everything to your images. So those post-processing things can also be done. You just need to find a perfect plane, if that particular plane is in focus or not, and then you just start and do your imaging. Okay, so this is how simply one microscope, a system of microscope, modern microscope will look like. Nowadays, there are microscope which will like open at the top, which will like, you only have to place a sample inverted top around. So all of them depends on how you want to look at. There are also kind of microscopes where you immerse it. So these are like oil immersion based microscopes. These are nothing but used to improve the resolution of your imaging. Okay. Then I don't think so. There are some. Okay. Yes, there's this word prism. Another word, beam splitter. Okay, binocular is like two ways. So what is this prism? Prism can be nothing but, oh, now you know what a prism is, but okay, 3D view of it. But it can be used to split your beam, light that you are sharing. Similarly, beam splitter also. It splits your beam into two halves or three halves or n number of planes that you want to looking at, and nothing but the light which is now diffracted through them or nothing but passed through them will now have different properties into it with respect to the specimen that you're trying to image. So it is not also regarded to a different kind of microscopy. So we'll see it how it goes. Okay. So that was how it was. And now these kind of imaging, what is still this stage is nothing but called as bright field microscopy. Okay. Always if you go, the basic ones is this bright field microscopy. Now, if someone can unmute yourself and say up that what happens in bright field microscopy, or which kind of specimen do we image in bright field microscopy? Is it any, just a random guess is also fine. Anyone?
Beam is used, then it is a bright field microscopy.
Sorry?
When the direct beam is used for illumination, then it is a bright field microscopy.
Yes, exactly. And about the specimen, if you'd like to comment on. Okay. No way. So we'll see different kinds of microscopy in this for the slides. You'll be able to understand that okay, how and why, which one, how which type of specimen can be used for them. Okay. So now this is like Kohler illumination. So you can read about this Kohler phenomena. It was also there in our 10th and 12th. So it this is some type of microscopy which is referred to as reflected light. Now, if you see reflected, there is also one part that's transmitted. Okay. From reflected, what we know is something that's reflected from the surface, right? It can be also reflected from below, from the sample of it or from the body of the specimen. But now here from reflection, we just see from where the reflection happens. Reflection happens only from the surface. From where transmission happens, it is transmitted and then you receive the light through it. Okay, so it is always regarded for surface in these cases. Okay, now what happens in these cases? You always have a beam splitter here, and there are only two ways. You always see where your objective and where your this condenser lens or what do you say? Yeah, so one which illuminates your object and another which is able to is which helps for image formation. So where both of these two lenses are placed. So here you have this one, here you have these lenses. So condenser and objective lenses. So both are nothing but placed in the side of the specimen, okay, towards the side of the specimen. So here, whether it's a function of energy of that particular signal, what you're trying to see, it's always a top down approach, how it follows. So light is nothing but reflected to the specimen, it's focused, illuminated, goes to the object. Now here you will use a beam splitter and it goes. Okay, so one can also assume the flow to be this way, one can also assume the flow to be this way. Okay. And then finally, what you image is nothing but goes up and you make an image through them, right? So this kind of samples usually is used for opaque materials. Now, what these opaque materials can be, something which are not completely transparent to light and light cannot pass through them apparently. So these are nothing but materials which are usually less than 30 microns, and they'll have their surface which is surface is nothing but reflected through them. So that's a very simple phenomena for how reflected light microscopy happens. To the another way, if you see this transmitted light microscopy, in transmitted light microscopy, you have these on either side of the specimen. Okay, if you see here, these are nothing but on either side of the specimen. Here it's oil immersed. So what happens in this case is you'll get a higher resolution. But this is nothing but it's for the specimen for such things where your specimen is nothing but transparent to the light. So it is nothing but very particular to biological samples where you even want to see like let's say cells or bacteria, something like that. So in those cases, you can see these samples very accurately. Whereas in the other case where you saw, it was nothing but very helpful for materials as polymers. This one's like fibers or something. Then you can have metals into it. Then you can have something as paper. Okay, so all kind of these things are nothing but they are not light transparent. They always have that inherent property attached to it. So light cannot like see through it. That's why it's essential that we use light is nothing but opaque. The medium we split it into two and then we image it. Whereas in this case we have two other places. So the both of the lens are placed on two different fields of your imaging view and you image them. So this is like always with respect to the sample that you're trying to image. Okay. Now, in this cases, if you directly understand now that what happened in reflected and what happened in transmission was nothing but places of your objective as well as your condenser lens, right? Now, where your objective lens were directly transmitted, objective lens as in here, if you see, they are nothing but the beam is directly going to the specimen that is placed over here. Yes, beam is directly passing on to the specimen, so that's a direct beam. You get a diffraction, you get a contrast to it. The contrast is much more higher in this case. Whereas over here in the transmission case, what happens if you I'll show that you later. Okay, so what happens in this case is everything is passed on to the sample. So if I have two samples, I have a slide on it, but I guess that's later. So something which is very polished, all of your light will 100% be reflected, right? Something which is not, some light will go, some will go even over here, some will go, some will reflect back, some will go, some will reflect back, some will go, right? So in this case, it's even transmitting, it's even reflecting, transmitting, reflecting. So you have like scattering, absorption, everything in play. When this happens, you cannot get the level of detail what you want to, but the contrast of the image overall decreases. So our human eye won't perceive it that okay, there's a difference. However, you'll see the difference, you know, okay, there are differences in there. You assume that there should be differences, but you cannot see them how microscope differentiates them. So what happens in those cases, people have differentiated it in terms of two kinds of fields. So you have a bright field and then you have a dark field. In terms of this dark field, what happens? You take a diffractor, and based on this diffractor, the beam, how it splits, it gives you contrast on the other hand. So this is nothing but the diffracted beam helps you give this dark field over here. So in this case, your initial beam, what's passing through this is directly going through. But in this case, it's traveling through. So your first order, second order, everything will pass, but your zeroth order beam won't pass it through. This zeroth order beam is nothing but very essential for your direct illumination of your object or your specimen, which is lying next to the condenser lens, and which is how affects your contrast of the image, right? Now, when you do so, people can also improve the contrast of these kind of images. They can use always, they can subtract the background. So there are image processing techniques as of now. While subtracting the background, you'll get higher contrast. You'll also won't improve resolution though, because last time how we saw people were confusing between resolution and magnification. So that is like whole set of different things, which again depends on your aperture. But this we are only talking about contrast in here. Okay. So now actually what contrast is and why we need contrast? Because the specimen that we follow are nothing but the biological specimen or material samples, or let's say you made a hydrogel, something like these scaffolds or something, and you want to characterize a little bit part of it. These samples are nothing but they are thin and transparent as well as difficult to see. So one can always stain them or do this contrasting techniques. Now where and how contrast comes into play? If you look over in this last image, you get no particular differences in here. Like the differences are almost getting diminished to an order. So what contrast is nothing but the difference in between this scale, difference in between this scale by the average of it. So that is nothing but a difference in color that you can distinguish, a difference in luminance level that you can see, right? So for an let's say if we want to define it in a qualitative way, how we can define contrast is it can be differences in luminance, 2 minutes. Okay. So it can be difference in the luminance by your average luminance. So this is how you can always qualitatively define that, okay, how your contrast is coming through. So that is nothing but if you have, let's say last time we saw that what's a pixel, and if you have a 8-bit image, you have like 2 raised to 8. So that is nothing but 0 to 255 bits in your image. Now your 0th one will nothing but correspond you to the darker one. Here we can say the lighter one. So in those cases we say that okay, the darker one minus the lighter ones or the whiter ones by the average of it or the lighter ones. That is how gives you a contrast in a particular image, what's happening in there, right? But this is always not the case. How people always see it is, let's say if this so area that is this particular circle following through is your specimen that you're trying to see, and the outer one is the background that you're trying to see. How you define contrast in this particular case would be your specimen's intensity minus your background's intensity divided by your background intensity times 100. But this kind of techniques you cannot always like define it or give you a exact value that how much contrast it's going to give you. So that is how you always need some kind of different kind of imaging techniques, which are like this differential interference contrast, or there are phased, there are polarized methods. So we'll see how and what difference these techniques make. Okay. So here we see that, okay, there are surface reflectance from this particular plate. Okay, I guess. if my pointer is visible to all of you. So if it's a white paper, light would almost be reflected and you have a lighter region around here. And that's nothing but 10% absorb. But it's a black paper, we always say that black things always absorb more light, more radiation into it. So it's highly absorbed. So you cannot always see the reflectance through these particular substances which are like darker enough, which have a field to them, which are denser enough. So then you need some methods through which you can differentiate them. So this image is from Professor Slides. So if we see that if we do a bright field microscopy, you see that okay, these strands are highly visible to you. But when you do a dark field illumination, something that's refracted from the side and you don't no longer get the 0th order beam directly passing through the aperture now or through the specimen now. So you can always see that there are these darker sides in here. Now if you again remove this darker sides, or it's like subtract the background from here, you can essentially improve the contrast of this particular image. But if you don't do such, it's like here you're only able to see the strands over here. But here if you see, you're also able to see the structure of it properly. But again, the resolution is not that great in this term, because what's happening in here is like we're not, so these, the first one is nothing but your direct imaging. Second one is something which is processed, and again you have some role of the diffracted beam. But when you don't have the role of diffracted beam, you also apply some image processing algorithms, you get something image like this, which is nothing but cross polarized. So you'll see how, so there's one part of it just to measure it, just to use the instrument. Second part of it, how you can again assess or enhance the imaging that you're trying to do. Okay. So following it, you have this first one, that is nothing but phased contrast microscopy. The only one thing what happens in phase contrast microscopy, if you just see, it will enhance your contrast, right? That is what we are trying to do from starting. So contrast in what kind of samples? And so let's just like start from the first. So this samples or specimen would be transparent. These can be unstained, because now you just want to see what's happening or what's the difference of phase in your direct specimen. And what happens here is like the phenomenon of it. When light passes, the phase changes. So the phase shifts. Whenever this phase shifts of the light passes, you get a change in intensity. Right? So whenever this light is passing through this, you get a change in intensity. Now, how and why it's happening? Now, your light is passing from this particular source. It is now shaped through this annular ring, this particular ring right here, this ring right here. And this ring is nothing but shaping your beam, how it's passing through your sample. So now it is nothing but when it's passing through your sample, it's again diffracted over here, again shaped through this annular ring, will nothing but go and form an phase contrast image. Now, in that phase contrast image, what happens is the phase shift will again cause the undisturbed light to move by 1/4 wavelength. This 1/4 wavelength will allow this constructive and destructive interference to happen. Okay, now when this interference happens, you get an image over here, right onto your plane, right? So that image would be nothing but highly in contrast, and you also no longer need to stain your sample now. It's like, or do any fluorescence kind of imaging. So that's how like a very simple approximate of it. So first is nothing but you pass the light via the light source, shape your beam through these annular rings, you pass it through the specimen. Now its light is reflected. Again, you have those annular rings. After that part, what happens? The light which is not phase shifted anymore, you phase shifted by 1/4 of the wavelength. Now, why 1/4 of the wavelength? That's a question that, based on the aperture, the grid spacing. What's the grid spacing in there for the amount of light pass through it? So that spacing would be eventually dependent on this particular wavelength. If it's higher or lesser, you'll eventually have artifacts for the same. If it's lesser, if it's good, if it's not, it's bad for your imaging, right? So in this case, it's 1/4 of the wavelength, and then accordingly to this 1/4 wavelength, you'll have constructive destructive interference, as in how you'll get an image that is formed through your source. So that's how phase contrast imaging works. Okay, any questions? Okay, I guess not. Then next one is this differential interference contrast. Now, in differential interference, if you just see the first two words, because last is nothing but contrast schematic. So what do we actually want to get over here and how it's getting? Differential is always related to gradients, right? And in this case, what happens? You take a polarized light source. So you have this light source, it's being polarized, you pass it through a prism. Now that's special prism here. What do this prism do? It will generate this sheared light waves. The sheared light waves are orthogonal to your sample. Just using the terms that are written over here, you get a beam how your light is passing through the lens. Okay, is orthogonal to the specimen, passes through your objective lens, focuses it. Again, you have your prism, forms light, again combines the light into one particular source, and you analyze it, and that's your image. That is nothing but you have a higher contrast over here. So that is how the optical path of generating the image with the increased contrast was. Likely how you get it is nothing but it's a pseudo 3D image. And this type of imaging was also very useful in unstained biological specimens, and it will help you reveal finer details in mediums which have the variation of refractive index. Right? So it will help you reveal the differences where you have a medium where there are like one is denser, one is lighter. So you can see differences in between those kind of mediums. Now there's a goal or task for you that, okay, if you are more curious enough, you go and look how this prism works. It's might be different from our regular prism, but if you know the principle of our regular prism, you know that, okay, how lights it's splitted. Now it will help you split your light into two such planes. Now that two lights are nothing but orthogonal to the surface. This is somehow a principle of bright field microscopy, but using a polarized light, then you differentiating the light into two using the gradient of them, that will help you increase the contrast over here. And eventually, in a medium which have different refractive indexes, your contrast will also increase. So just follow the words along, you'll understand how the phenomena is working. Right? Now, there's only one difference in between this DIC microscopy and this polarized light microscopy. What's that difference? Here you used a polarized source. Here is you're also using a polarized source. Here you were just passing it through a prism, right? Here you're not. When you're not passing it through the prism, what's happening is there are difference in phases. So phase shifting is happening. Because of the polarized light, it will pass through a specimen at different planes, or where you have a sample, such as you have different cellular planes, or let's say you have some fibers or spindles, something like a muscle. When you're passing your sample through those, there is a change in phase. That change in phase, nothing but will eventually give you a polarized light image. And that image will have an increased contrast with respect to your dark field microscopy or your bright field microscopy. So that is how this four kind of microscopy works. If you have any questions, you can let me know, or we can go to the question and answers session.
This halo effect inside of effect, that bright and dark rings are formed around the features of the specimen.
Yes.
So that
Yes.
region is what is happening. Is it transition from the change in the refractive index of the surrounding and the sample?
Yeah, you can also say that, but it can also happen due to the change because of the diffracted beam, how it's passing through. So that also affects it. So
So
that
that
phenomena
is
can also be
that.
related to the airy rings. Yes.
So at the interface, what is happening from once we are moving, maybe on a very small level, we see from a specimen to surrounding, we are moving. Then what is happening there? That ring is forming.
Which interface to from the specimen to the
From,
objective lens or from the light source to the condenser
no,
lens?
no, no. In the specimen, suppose there is a specimen and there is surrounding. In
Okay.
case of transparent biological samples, there is a specimen area where a specimen is there, and then surrounding is there. And once we are passing from a specimen to surrounding, this is happening. So what is actually happening at the minor, very small scale?
Yeah, so those are nothing but properties or medium properties. Because of your medium, the light is causing to have the shifts. What we can do on our end is like we can change the play in the outside material. So we are forcing the light to pass through a different kind of prism, have a polarized light, have a different phase shifts after it. But everything what's causing the changes is because of your specimen itself. So if your specimen is like having how we saw, if it's stained, if it's unstained, if it's a homogeneous medium, or if it having some structures like fibers or spindles, it will have such changes accordingly.
Okay.
Any other questions?
This is this the 3D effect is coming in this DIC.
Yeah.
Depth perception. That depth perception.
Yes.
So that is coming because of what?
So that's because here, when you have the prism split your light into two different sheared orthogonal ways. Now, if you understand by sheared waves, what happens, you have two different parallel beams that are going to the surface. One is like at a lower interface, one is at a higher interface. That is causing you give your sample a look which is like 2D but orthogonal to the projection plane. So that is how you get a virtual 3D image.
So that is because of sheared wavefront.
Yes, exactly. Here. Okay. So if not, then we'll go to the assignment tab. I guess yeah, this week's assignment is due tomorrow or day after tomorrow. So these questions are more or less similar to your this week's questions. So the first one, which optical microscopy mode generates better contrast? So we had like two modes here. Which were the two modes?
Dark field, bright field.
Yeah, and which one gives us a better contrast?
Dark field.
Yes. Why?
The background, we are subtracting background, so in the brightness part of the bright field goes out.
Okay. Any other parts into it?
In case of dark field, we are using 0th order diffracted beam.
Exactly. Okay. The zeroth order beam is something which is playing a role, how it's differentiating the bright field and the dark field. Okay,
Right.
next one. Which one is correct for the reflected light microscopy? So this we just saw now through the schematic. How are the light source and the objective lens placed? Like two different sides of the specimen on the same side of the specimen, or objective or condenser lens at the same side of the specimen. How? In the reflected light microscopy.
The same side.
Sorry. Reflected microscopy. Yes, exactly. In the same side of the specimen here. Which one is true for bright field microscopy? So just a direct difference in between bright field and dark field.
First one, A.
Yes, only a direct beam is allowed to pass through the objective lens. So however, in case of dark field, it's not the case. Specimen with extremely small thickness and opaque specimens are respectively required for what? So there are two kinds of microscopy we saw, transmitted and reflected. Which one's for which one?
For a small thickness, we can have transmitted.
Hmm.
The opaque will be reflected.
Yes. So for small, you can have transmitted, opaque, you can have reflected ones. So that's your D. There are optical tricks that we just saw now, the arrangements, things as the prism, the annular rings, all of those, which are nothing but only used to amplify the contrast difference. So, in which kind of microscopy we do those things?
First one.
Yes, exactly. In phase contrast microscopy, in differential interference contrast microscopy, we do this kind of things. Okay, so trying to say something. All right. Okay. Okay. There's this depth perception or the pseudo 3D effect that just now a student asked is provided by which mode?
E.
Someone trying to say something. All right. Okay. Which one?
DIC.
Yes, exactly. Okay. This halo formation that we just asked is appears in which kind of microscopy?
The phase contrast microscopy.
Phase contrast microscopy. That is because the amount of diffracted beam will directly go along with the direct beam. So that is how the central spot will remain higher and somehow the halo will reduce according. Okay. There are two. Okay. I guess this was okay. Then. So something with respect to polarized light microscopy that we have a polarizer when we give the light source, we have an analyzer towards the end for the image formation. I guess we didn't really look on how where the analyzer was, but this was for polarized light microscopy.
In this case, this analyzer is recombining whatever polarizer has given us two beams,
Exactly.
orthogonal beams. It will recombine
Yes.
in analyzer.
Yes. Which of the below is used in differential light microscope interference contrast microscopy?
This B.
Yes, the prisms,
Yes.
specialized prisms. Polarized light provides you information about
Multi-phase material by refrigerance.
yes, it gives you information about multiphase. What is this one? Depth perception?
That's a DIC.
Yes, and this one through fluorescence, this one for
Fluorescence
all
is
different
fluorescence
micro.
microscope. Yeah,
Yes.
biological assessment transmitted one.
Yes. Now, if you have a very fast excitation and emission with no time lag, so that is shown by which microscopy?
Fluorescence.
Exactly. I guess you guys know everything. If we have excitation and emission signals differentiated in fluorescent microscopy, so that can be done by. So assume it's like think this of a beam splitter. Sorry.
Dichroic mirror.
Yes, by a mirror. So that will help you split your beam. Differentiated. So which of the following statements about phased contrast microscopy is true? Does it rely on staining techniques or if it uses a fluorescence filter or not for live cell imaging or it's primarily used for transparent or unstained samples?
One.
That's option B. We just saw it. That for transparent and unstained samples so that you get the finer details and how how your specimen causes the phase shifts and accordingly you can map the phase shifts to your sample. So you no longer need to stain your samples for it. Okay. Then so this I guess I didn't see it anywhere, but okay, if you guys know. So these images are created using stimulated emission depletion techniques. I haven't read about them and I haven't spoke about them in the session also. So next week we'll look on in this particular thing in more detail. Okay. So that is stimulated emission depletion technique.
Okay.
Last one. Do you know what happens to the light passing through different parts of the specimen, which is in phase contrast microscopy?
That's a B.
Yes, it undergoes phase shifts due to variations in the refractive index. Okay, that's it for the session. If you have any questions, you can let me know. Done.
What's the function of lambda plate?
Sorry?
Lambda plate?
Okay, I'll just go to the slides. It's not exiting. In slideshow. So lambda plate is also something as similar to your beam splitter, or if I like to say something as similar to your prism. Oh yes, it asked me to read the annotation. Presentation. Okay, let's see if we have it in any of the microscope images. Yes, it's not here. We'll see. Do we have it in lecture slides where there's a microscope example where the lambda plate is used? I've used it
Yeah,
in yes.
just before this analyzer, there will be lambda plates.
Okay. So in the polarized one or the phase shifted one.
Yes, yes.
Yes. Okay. I guess then I'll see those examples and then we'll accordingly show, because the ones that I have, in these I don't see a lambda plate, but yeah, it's eventually used towards that side only to um convert probably a form of polarization to another form. Probably that part how it's playing through is like based on the wavelength of the light, it will convert your probably how it goes, your linear to circular or circular to linear. There's a difference in polarization, so it just converts it and then the analyzer helps us to compute it, and finally you have your image.
This, what is the Stokes shift?
Sorry,
Stokes shift
Stokes shift where?
that comes in fluorescence microscopy.
Oh, okay, that I haven't covered this week, so we'll see it in next week if it's there. I'll
Then
write it
lecture
down.
also in the lecture also the professor has covered this whole the phenomena, but he has not named it.
Oh,
And
then
there is
I
a
guess it
question.
would be interesting. Yeah,
There is a
yes.
question on this, but he has not named the phenomena. He has explained phenomena beautifully,
Oh,
but not named it because this is a Stokes shift. That is not named in the lecture. And there is a
huh.
question on a Stokes shift. So
Oh, you can write in the discussion forum then. They probably will change the
yes.
question or will make that question as graced ones.
But one can understand from some other source that this is called a Stokes
Ah,
shift. He
yes.
has explained that there is a change in wavelength of emission rays
Mm-hmm.
because lower energy, so higher wavelength will be there. Then excitation rays, and that shift is called a Stokes shift. But he has not named it in the lecture.
Okay. Okay, then likely, I guess, preferences, then probably he would name it something else.
Yeah.
Okay.
This also this dark field contrast.
Mm.
There is a the halo region. That
Mm.
why it is happening is because of matching of refractive index from one region to another.
Difference in, yes.
Yeah, so it's a matching that at the interface it is matching is happening from one refractive index to another refractive
To
index.
another, yes. And then when it's
That
changing, it's
that's
here.
my guess, but there is a question on this where matching word is used, refractive matching.
Well, I guess that's a trick then. If it's in this week's, let's see.
This assignment will be after every week or it's intermittent
Yeah, assignments are every week.
every week?
Yes, yes. Every week you'll get an assignment. After 4 or 5 lectures, you'll get the assignment. Which question were you saying?
First
And this
one.
all we looked at here.
First.
Belows are occurred due to overlap and misalignment. Oh, okay. That's a trick question. Trick
So it's a
option.
matching
Trick
reflection.
option. Yeah. Yes, that's a trick option. Yes, you don't need to worry about that too much. Okay. So questions are only like moved here and there. The answers remain the same.
And the other thing is that in this dark field, this contrast,
Hmm.
your this contrast is generated by a scattering of the light direct beam.
Yes.
You are not allowing direct beam to pass through objective.
Pass through
You are
it.
only
Yes.
allowing zeroth order diffracted beam to pass, but intensity will be very low there.
Yes.
Yeah.
Yeah, so these concepts are like pretty easy if you just go and see how the optical path for the same follows through. If you understand the optical path, then there's like no more differences for you to understand that, okay, how it's going wrong or where it's going wrong. Also, through that way, you know that, okay, what are the tiniest or detail into it, which particular parts are involved into it, instead of just seeing that or just memorizing which kind of specimen or which kind of sample it's used for, but also remembering that how these values or parameters are, because when in real life you just have a microscope in front of you and you're like, okay, I want to do a bright field microscopy or a fluorescence microscopy. The technician might help you around with it and you'll just image it. But if you know the exact details of it, the planes of it, focusing of it, how you change it, how resolution matters, how magnification affects, you'll be able to get a pretty beautiful image, a wonderful image through it. And again, doing the changes in the software, this background correction, correcting for the exposure, these settings. If you understand the physics behind it, this is like, okay, imaging your specimen won't be a problem for you. And you know that, okay, for this particular specimen sample, which kind of microscopy technique would be proper for my imaging.
Yeah.
Okay, so that's it from my side. If you guys have any questions further, you can let me know. Else, thanks for joining today.
Okay, thank you.
Thank you. Okay, so if you don't have any further questions, then I'll end the session for here. Thanks for joining. Thank you.
Thank you, ma'am.